Hello everyone, welcome back to my channel. Today let's go over a medium question that I just resolved on my own after a long time. So I'm super happy that I was able to come up with my own solution to this question without any assistance. So let me show you how I did it. First, it looks like I solved this 2 years ago and I tried it like 7 months ago and I was able to redo it just 10 minutes ago. Couldn't do it 7 months ago, so I don't know what's going on there, but I'm just happy that I was able to do it without any help today. So this is 209 minimum size subarray sum. So return the minimal length of a subarray whose sum is greater than or equal to target. If there's no subarray, return 0. Pretty straightforward question. Find the subarray that greater than or equal to target, the sum of the elements. So 6 here, 8 here, vice versa. So obviously my idea, you can do it n squared, but my idea was to use prefix sums. So this is just accumulating nums. So you get, so now you would get 2, 5, 6, 8, 12, 15. So accumulating. And then now the idea is to pick the number, any number that's bigger than or equal to target. We need to find anything to the left to subtract the difference. So for example, 8 is bigger than target, right? So 8 at index 3. So 8 minus 7 is 1. That's going to be the difference. So let's find the closest index to the left of 8. That difference is greater than or equal to 1. So if 1 is the difference, for example, if we do 6 minus 8 minus 6 is 2. 2 is not bigger than target, so it has to be, in this case, 8 minus 2 is 6. You can't do it, so then we don't care about 8. So in this case, we go to 12. And in this case, it's going to be 5 because 5 is exactly what it is. But so 12 minus 5 is 7. What about 12 minus 6? You can't. 12 minus 8, you can't. So for 15, 15 minus 8 is 7. That's the smallest subarray sum because 15 minus 8 is the sum of this subarray. That's of length 2, which is why we get this answer. Okay, so hopefully that made a little bit of sense. So find the elements that are bigger than or equal to target, and then find the nearest index to the current thing to the left that is at least of the difference. So let's go for I and enumerate nums. So if P of I, because we have to look in this list, is bigger than or equal to target, then we have a difference, which is just P of I minus target. That's going to be positive because this is bigger than or equal to the target. And then what I did is a bisect right on P with the difference. So let's go ahead and print VL of I. This should be to the left of I. And we're doing a bisect right to get us close because bisect left is going to find the first element. So for example, if you have 3, 3, 4, 5, bisect left is going to end here if you're looking for 3. If this is 3, bisect right would end here if this is 3. So as you can see, 5 minus 4, but these are indices and lengths are 1 more than indices always. So let's just go ahead and say we want to minimize something. Nothing is going to be bigger than infinity. So minimize answer with I minus BL plus 1, and then return answer at the end, right? So if answer is still infinity, then we return 0, as it says there, because there is no subarray that's valid. And let's just go ahead and go through these. As you can see, it's 1, 2 minus 2 plus 1, 1 minus 1 plus 1. In this case, nothing. Okay, so let's run this. And this is O of n time complexity now. Actually, O of n log n, because binary search takes logarithmic time complexity, and then looping through the array is n. Okay, so let's go ahead and submit this. And there you go, passes all test cases. So again, I'm super happy that I was able to come up with my own solution to this problem without any help after such a long time. So that's it for this video, and thank you for watching.